So like the trapezoid rule, we're going to go ahead and derive Simpsons rule. It's another rule that's used for finding the area under a curve between 2 points A and B. And so here again, I just have this sort of generic curve just to sort of visualize how the rule works. So in the past, what we've done is we've split up that area into several subintervals. And in this particular case, I've got 6 of them. We first began this chapter by then splitting that into rectangles, which, as you can see with rectangles, since the top is flat, we end up having a lot of either under or over area. And then of course, the more rectangles you squeeze in there, the better of an approximation you get. But if we're doing these by hand, it's kind of difficult to squeeze in like 50 rectangles. So then a better shape that we could use, and that we have used, are trapezoids, because the top of a trapezoid can be on a diagonal. But even still with trapezoids, you'll still have a little bit of under or over error because they don't quite curve. They're still straight. They're a much better approximation, as we can see here, but perhaps maybe there's one better. So that begs the question, is there a shape with a known area formula? Because that's the key. It has to be something whose area we know that could better fit inside a curvy function, even better than a trapezoid. And the answer is yes. I don't know if you've ever heard about these shapes before, but there's a shape that looks kind of like this, where the top is parabolic. It's curvy. It's not straight like a trapezoid. And there is a formula for the area of the shape. And the formula is this right here. It's h over 3 times L plus 4m plus r. So you're probably wondering, what the heck does all of that mean? Well, L is this left vertical height here, L for left. M is the middle height, and R is the right height. So it's kind of easy to remember left, middle, and right. And then H, like usual, is our sort of horizontal distance, and it's half of the base of one of these parabolic shapes. And in order to fit these shapes nicely underneath a curve, we need to have an even number of subintervals, because each of these shapes has 2 intervals. So plugging it into, or putting those shapes under our generic example, it kind of looks something like this. You can see I would fit, over these 6 intervals, I would fit in 3 of those shapes, because each shape requires 2 intervals. So let's use this generic shape to go ahead and derive the formula for the area under this curve. Well, first thing I notice is that the height of each of these shapes, or not the height, excuse me, the h value of each of these shapes, like with the trapezoid rule, is just simply the change in x. It's the distance between each of these x values. And so the way that we have found that in the past is we take the entire distance from A to B by subtracting b minus a, and divide that over the n subintervals, and that'll give us an even distance between each x coordinate. Secondly, we need to sort of figure out how to find the L, M, and R from the area formula. So just as a quick reminder, L, M, and R are those 3 vertical heights of the shape. Well, like with trapezoid rule, we just take our x coordinates, we plug them into the function to figure out how high they go, and we get those as our heights. So for example, with this first shape, my left height would be f of a, my middle height would be f of x1, and my right height would be f of x2. So to find the total area under that curve from A to B, I would find each of these individual parabolic shape areas. I've got 1, 2, 3. Add it all up, and that'll give me the entire area. So let's go ahead and do that. With the first shape, I would have h over 3, because each shape has h over 3 times the left height, which in this one would be f of a, plus 4 of the middle heights, and that's just from the formula for the area of this shape. So my middle height is f of x1, and then plus the right height, which is f of x2. So this here would give me the area of this first parabolic shape. For the second shape, again, we start with the h over 3, and again, that's just from the area formula for these shapes. My left height would be f of x2, My middle height is f of x3, so I have 4 of those. And my right height is f of x4. For the third and last shape, again, I start with h over 3 because that's from the formula. And then my left height is f of x4. My middle height is f of x5. I have 4 of those. And my final height is f of b. So you might notice that with the trapezoid rule, some of these heights were used more than once, or for more than one shape. And in this generic example, I have f of x2 was my right vertical length for the first shape, and then it was my left vertical length for the second shape. So if you notice, like, every other f value is going to be used twice. The middle ones will not, because the middle one is only used for one shape because it's in the middle of a shape, so it won't end up being an edge of another shape. And so there will always be 4 of those, and that's just for the formula for Simpsons rule. Whereas those interior edges are going to double up because they're going to be used for 2 shapes instead of just 1. So when we combine our like terms, so again, each of these had an h over 3, so I factor out the h over 3, and I just add up all my y values. I have f of a, 4 f of x1s, and then 2 f of x2s, and then 4 f of x3s, and then 2 f of x4s, and then 4 f of x5s, and then f of b. So I want you to notice another thing too to sort of help you memorize is the coefficients of these f values alternate. They always start with 1 because the edges or the endpoints are only used once. So f of a and f of b are only used once. So it always starts with 1, and then that first interior f value is the middle of that first shape. So it is used 4 times. And then this second interior f value is used twice. It's the right height of the first shape and the left height of the second shape. So you go 1, 4, 2, and then it alternates. 4, 2, 4, 2, 4, 2, 4, 1. And notice the second to last f value will always have a coefficient of 4 because it'll always be the middle of that last shape. And so the middle of any shape is multiplied by 4. And then as a reminder, the way we find the h value is by figuring out the total distance from a to b, dividing that into n subintervals, and that'll give me the h value because h is just the length of one of these subintervals. So let's generalize this for any number of subintervals. So in this case I had 6, but n could vary and be any even number. So you'll just basically notice that it has the h over 3 on the outside, and then the coefficient of f of a is 1, and then it alternates 4, 2, 4, 2, 4, 2, yada, 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 4, 1. Again, that 4, or that second to last f value has to have a coefficient of 4 because it will have been the middle of the last shape. And then again, the way we find h is by doing b minus a over n. So now you have yet another thing to memorize because you are required to memorize Simpsons rule. But the better you understand where the rule came from, the easier it will be to remember it and to remember why it alternates 1, 4, 2, 4, 2, 4, 2, 4, 1. So let's practice using the rule. So we're asked to consider the integral from -3 to 1 of x cubed minus 2x dx. We're asked to use the Simpsons rule with n equals 4 to approximate its value. So it always helps to look at the graph of a function. So here's our graph of x to the third minus 2x. And I'm only really concerned about this graph from -1 over to 3. Next thing we want to consider is the number of subintervals we're using. So in this case, we're using 4. Knowing this, I'm able to find h, because remember h is b minus a over n. b in this case is 3, a is -1. So the distance between them is 4. Take that and divide it by 4, and so each subinterval will have a width of 1. And so I can see that here. There's a distance of 1 between each of my main x values. Then I recall the rule, or the formula, and just start plugging numbers in. So we found h to be 1. So I have that here, 1/3. My left x coordinate is -1, so I need to find f of -1. My first interior x coordinate is 0, so I find f of 0, and I'll have 4 of those. The next x coordinate is 1, so I'll find f of 1, and I'll have 2 of those. Then my next x coordinate is 2, so I need to find f of 2, and I'll have 4 of those, because that's my second to last one. And then my last x coordinate is 3, and so I need to find f of 3. So that works out to be 1/3 times 1, because f of -1 is 1, plus 4 times f of 0, which is 0, plus 2 times f of 1, which was -1, and then plus 4 of these f of 2 values, and f of 2 is 4, and then plus f of 3, which turned out to be 21. So the inside ends up adding up to 36. Multiply that by 1/3, and you get 12. So according to Simpson's rule, the area under this curve, or between this curve and the x-axis, is 12. Now, in your outline, you have 2 more parts to this example, parts B and C. I'd like you to do part B at home as like a U-try, and then together in class we'll talk about part C and how to find the error. I'll see you there.